All right, guys, let's get started. You must have a lot of questions for everything for the class since we just had one lecture on Monday, right? So regarding mastering engineering, it's also my first time to use it. But what I heard from students is it's you have to pay for the textbook first, which is $120 to get an access code. Then you can access all these homework problems. Is that true? I mean, I'm so sorry for that. It's just the only way they can organize all the three different sections. There are only two TAs. I'm pretty sure the TAs office hours will be posted to the syllabus and Canvas as well. So you can ask questions and find help from the TA and also from myself as well. I was thinking about like, what's the solution to this? Is there a better way to do it? So the best way to do it is just to keep the size of the sections smaller, like 30 students. I've never used the master engineering. The size of the classroom usually 25 to 30 as the maximum. So I usually just create every single homework myself, usually twice a week, including quizzes and homework assignments. I'll hand it back to students manually at the beginning of the class. So I know each student's name in the class by doing that. Usually it takes 1 week or 2 weeks, so I get to know every person's name. But I don't know if I should feel better or not. I know Sean, I know Matthew, someone else, but I probably won't be able to know everyone's name in the classroom. That's just what's going to happen. Since I won't be able to have the chance to turn it back to you and just call your name and return it back to you during the class. It's going to take me like 30 minutes to give it back to you, 100 students at the very beginning of the class. So that's what's going to happen. And mine is just one of the best schools in Colorado. You are taking that benefit here, so it's a trade-off, right? It's a pros and cons. It's a big classroom, and professor never know your name. And if you want to introduce yourself to me, welcome to do so, please. And again, I'm sorry I have to pay for the extra dollar to do the work. And sometimes there are other issues as well. So, like I said, I have taught this class for millions of times, but this time it's totally a different set of problems. But it's super simple, actually, to me at least. So I was looking at the way I'm going to teach this class is to prepare you guys for the problems for the tutors and homework assignments and exams. I printed out, since I have the access to the solutions, so I printed out all the problems, like with the view, there's a version of the view has the solutions just following the problem. So I just printed out every single one, the tutorial ones, the homework one. I just skimmed through all of them. It only took me 10, 15 minutes to go through every single one. And I just found out by far, okay, tutorial 1, homework 1, tutorial 2, homework 2, they are all just repeating problems. Ohm's law, power, energy, resistor, current, voltages, just repeating and repeating. So it's not very difficult. Don't get scared if you're seeing problem for the first few weeks. It's no new things across all the first few weeks. So if you're asking me how I can prepare for this class, just attend the lecture. If you didn't get it, watch the videos afterwards. I'm recording and posting my lecture to my website. You saw that, right? Let me show you again. So electronics, right? And then go to the first one. You can see the first lecture's video already posted. And I didn't bring my printer here, but I'm going to take pictures with my phone. It's not very difficult to do, actually. So the scanner will just feed the papers into it automatically and eventually generate the PDF. But by doing this, usually I have 10 pages of papers. I just take pictures for 10 pictures and send it as a batch to my email. I convert it to PDF and post it over here. So these are notes. You don't have to take notes because notes will be available. If you want to take notes in your class, which is okay. But the bottom line is don't distract yourself. I mean, I want you guys to pay attention. And also, another note, I was thinking about this, because it's a very big classroom and the background experience and everything is so diverse. Okay, the people sitting in the front row, usually they have a lot of experience with electrical engineering. If they came from no, not the case? No. Okay, but some of you guys knows a lot about electrical engineering, but I'm serving 90 students, 96 students, 99 I think, 99 students, not just the 203, okay? I'm gonna slow down, okay, a little bit. It's gonna be boring for some of you guys, already know a lot of the materials, but please be patient, since I have to serve 96, 92, 93 students in the classroom, okay? Feel free to ask questions. None of the questions are stupid. Any questions, just ask. Probably when you ask the questions, you are also helping other people to understand it. Okay, if the question is so simple, you make other people feel better. Actually, oh, he doesn't know it as well. So, which is great. Okay, we don't have time to waste. Actually, it's so many materials to cover. Even though they are simple and repeating, but I think I still should cover them. Oh, before I forget, there's another thing I just noticed. I'll probably let you know. First, I won't be able to go through all the calculations. If I see just a super simple linear circuit, like 2 resistors, 1 voltage, I look at the problem. I really don't want to spend my time to calculate the final results. Only when I think there might be some potential problems or issues, I'll calculate it. However, I found an issue yesterday. For homework 1, if I found it, I'm going to let you guys know, okay? That's one of the cons of using mastering engineering. So I use the equations that I have been using, just Ohm's law, super simple. And I got a solution, the final answer, to be 2.2 milliwatts. 2.2 milliwatts. It's accurate. I didn't run any numbers in the middle. However, I think the system rounded the number in the middle, some intermediate values in the middle of the equation, and it's getting 2.14 milliwatts. So I'm not sure if you put 2.2 in there if you are getting the correct answer or not, or getting the credit or not. That's another issue. But it's not a major problem because it's probably one of the 20, 15 problems having this kind of issue. How do we solve this problem? I have to communicate with other sections, see if we can fix it, change it. If we cannot, I don't know. I would probably, if I find it, I'm going to let you know in the lecture. I'll just let you guys know, put 2.14 in there. Okay, but you have to know how to calculate it anyway. That's okay because that problem has been repeated in many other problems. So you will be able to know how to calculate with other problems. It's not an issue. So you are not missing anything in terms of knowledge of calculating resistors or currents. Okay. Okay. Now let's directly dive into it because there's so many things to cover. And there's okay, tutorials. Tutorials are extra credits. You see 0 points with the tutorials. Please also do that. If you are losing points somewhere else, so I think that's making things a little bit fair. Okay, you are losing points because of the weakness or the bug of the mastering engineering problem, but you are getting extra credits during the tutorials. You know what I mean? So it's fair, eventually. Giving you some more points, extra points, to compensate it. Okay, that's the best we can do. There's no perfect solutions if you have 100 students in the section. Tutorials are 0 points, but still do it. Okay, still do it. Now let's start with tutorial 1. In general, okay, if you see a black box like that, it's trying to confuse you. The problems are trying to confuse you. So when you see a voltage label like that, it's not necessarily that the real voltage in the circuit is like that. You know what I mean? So they can say plus minus, but it's minus 5 volts. It's happening a lot in these problems. It's labeled as plus minus, but it's telling you it's minus 5 volts, which means physically, in the real circuit, it's going to be a voltage drop from left to right. Is that clear? I want everybody catch it, not just people in the front. Do you get it? Or just keep in mind, okay? So these problems will be repeated all across the first few weeks. So if you don't get it now, don't feel bad. Eventually you'll get it. It's super simple, like voltage and currents, just polarities. If you play with it for a long time, you'll get it. So plus minus is labeled as that way. It doesn't mean that physically in the circuit, you are getting a voltage drop, a physical positive drop from here to here. Because it could be labeled as minus 5 volts. It's just on the paper in the textbook. It's in the problem. They just label it that way. So how to deal with it? Because the voltages can be labeled as negative, positive, negative with different polarities. Currents can be plus, minus, different polarities. So either the one way or one method can solve all the problems. So don't have to worry about that. Don't have to memorize everything or anything. Just one strategy, one method to get everything done. What is that? I just convert it to the physical current and voltage drop. You know what I mean? Just convert it to whatever is happening, really happening on the circuit. It's just one case. Okay? No matter how you label it, but if you come down to the table, you got a circuit board built on the table. There must be just one voltage drop and one current. Just use that number to do all the homework problems. So for example, this problem, okay, it's labeling is plus minus 5 volts, which means the voltage drop from here to here is minus 5 volts. It's confusing people, right? So don't think that way. Convert it to the real voltage drop. And what is it? Left to right, 5 volts. That's it. Okay? Does that make sense? Since I didn't draw anything else in the circuit, I didn't draw it. So possibly the current can flow left to right, right to left. Doesn't matter, okay? So if someone labeled, or the problem labeled the current flowing that way and tell you this is minus 5 amps, what's the strategy here? Convert it to the real current. Just convert it to the real current. Okay, there's just one real current and one real voltage physically happening in the circuit, right? Okay, so what's the real current direction and amplitude? 5 amps. Okay, so eventually, for this component, doesn't matter if it's a battery, it's a resistor, it's anything. It could be a current source, it could be anything. There's just one physical voltage drop, one physical current flow. It's gonna be left to right, 5 volts, left to right, 5 amps. So now you can analyze. You can analyze and answer a lot of questions. What are they? Okay, is this component absorbing energy? You can see these words, these terms. I actually usually don't use it. I've never used a lot of things in the homework problem. Anyway, you should know how to do it. Absorbing, dissipating. I think it's the same thing. Or delivering. What else? Outputting.
Provide.
Yeah, provide, supply, right? That's what they use, usually supply. Voltage supply, power supply, right? I think they didn't use output, they just use a supply or deliver. That's what they use in the problems. So you know what they are, okay? Absorb, deliver. So now let's see these two situations. If this guy has a positive plus minus voltage drop like that, 5 volts, and current flow that way, which means current flow that way, right? Is this guy absorbing or delivering? Absorbing. Consider this guy as a battery. It's anode cathode. You got current flow into it. You're charging up the battery. If it's a resistor, if I'm going too fast, it's okay because I'm recording the lecture. Just go back to the YouTube video and watch it, okay? It's okay. So if this is a resistor, it's taking the current from left to right and it's generating heat. Okay? So it's absorbing energy, absorbing power. If it's asking you to calculate the energy, how to calculate the energy? It's power times T, right? Which is energy. And sometimes you can see the energy they use the omega. So another confusing stuff. So capital uppercase W could be power, right? P could be power. P could be power, and lowercase W or omega, or E. This could be energy in the homework problems. Okay. These equations, I think you can find these equations in different places. And one student emailed asking about equation cheat sheet. I don't have it, but I will see if other sections provide it. If they provide, I'm going to provide as well. I just use a copy. Otherwise, you just look at the notes, the textbook, the lectures. Also the lectures. Let me finish this one first, jumping back and forth. So now let me ask you. I already asked already, but let's repeat it. So is this guy absorbing or delivering? Absorbing. Dissipating or supplying? Dissipating. Okay, because absorb, dissipate, deliver, supply. That makes sense? So if it's delivering, it's generating it's a negative power, right? Oh, delivering will be negative power. In terms of that device. And this will be positive power. Okay? Lectures. Slides. I don't use slides. I don't use slides too much. Unless you force me to do so. Don't tell me what to do. Just kidding. If you need slides, someone likes slides. It's over here. So this whole lecture was copied from another professor who has taught this class here for a lot of times. So I'm asked to copy it into Canvas. So this is basically what he did, who is Dr. R. Morris, and you can see his office hours, and you can visit his office hours if you want as well. So we're sharing these teaching resource within all the 3 sections. And you can see, if you click modules, you're able to see lectures, right? So lectures are slides. So for the first lecture, which is supposed to be used on Monday, and I was trying to convert it to mine, but eventually I think I shouldn't because it's really his materials. So I stopped doing that. It's gonna take me a lot of time. It's just actual amount of work. So these slides will be used as a reference. If you want to look into the slides, feel free to do so. So starting from lecture 2, you will find out I stopped changing all the things in there. You can see it's Dr. Art Morris and everything as well, But I'll prepare you guys well because I'm directly teaching all these materials or problem from the homework. Okay, so that's my role here. If I teach something else and you are not prepared, you'll complain about that, right? So during the teaching evaluation, you want to say, hey, just use other people's slides. No, right? I'm using notes. These are just references, okay? Just let you guys know. Let's move forward with other things, equations, because not everybody has that much experience in this field or area. P is VI, right? V is voltage, I is current. R is V over I is V over R. Okay? So, if you plug these parameters into P, you are getting P is also V square over R or I square R. That's how you can calculate it faster in a lot of cases. I don't want to make this class math heavy. If you see there's like an integration problem, which really testing your like Calc 1 stuff, feel free to use the online integration calculator. To be honest, one student visited this morning. I just told him, I've never done any Calc 1, Calc 2 stuff for 10 years. Just click. Okay? There are just so much, I can justify it. Don't laugh yet. There's so much electrical engineering stuff to be covered. You want to spend like 30 minutes to solve a integration problem manually? It's going to distract you from learning all this important and interesting stuff. Don't do that.
I think that laughs because we all know this website.
Oh. Bring it back to your freshman year. Yeah? Okay. It's not too bad yet, okay? If you look at all the problems, there are only like 11 homework problems. But adding those tutorials, maybe 20. And I finished all of the tutorial 1, tutorial 2, tutorial 1, homework 1, tutorial 2, homework 2, within like 30, 40 minutes, I think. So it's not making my sabbatical life too bad, I think. I'll just go through all of them and teach it. Let me find more problems over here, okay? Oh, Q. I is Q over T. So if you grab a piece of conductor, so the conductor's like a wire, piece of wire over here. If you grab a cross section in the middle, so it's a unit time amount of charges flowing through that cross section during the unit time. I think that's standard units are seconds. This is coulomb. Coulombs, and this is amps, right? Amps, ampere. Usually we just say amps. Okay. So during the class, I will ask you guys questions regarding the currents, the voltages. So as an electrical engineer, you want to answer that with the professional terms. Okay. So because most of the circuits we see every day, they are low voltage. Like laptops are taking usually 12 to 20 volts. And all the little embedded systems are usually like a 5 to 0.3 volts. So if you take a 5 volts, for example, and we don't want to drain a lot of current from the circuits, so we use like kilo ohms. But you know, because all these are circuit one problems, you are seeing a lot of bad values in there. It's just for calculations on the textbook. In real life, you will never see them. Okay. So for example, if I do 5 volts and 1 ohm, who is going to do that? It's going to draw like 5 amps. Okay, and one ohm is not doing anything really. It's very similar to like just short circuit. If you, for example, you got a ground, you short of 1 ohm over here to the ground, the whole circuit is not even able to like notice that. It's like treating this guy as a ground. You know what I mean? So usually we don't use these little resistors. So the most common resistors are usually like a 1K, 10K, 5K, or the smallest one I have used, commonly used, will be like 300 ohms, and they're being used as a protection resistor or current limiting resistor. Why? We don't have a lab here, but you guys should know current limiting resistor. So now this brings up another question: why do we need the resistors? It's a very big question.
To make sure that we supply the correct amount of voltages to, or the correct
Yeah.
voltage to a component.
Sure, that's definitely one of the correct answers. There are just so many ways to use the resistors. You can use resistor and voltage dividers.
You can use like a shunt resistor.
Shunt resistor as well. Yes. Okay. So you can deliver correct voltages. You can deliver correct currents as well. Okay. It's being used in many places. I had this question, and I never thought about it, but one high school student asked me during the workshop. That's why I think it's good to bring it up. Okay, so we use resistor for certain goals, to meet the goals in the circuits. For example, you'll see LEDs a lot in all many places. You got a power supply, you got a resistor, you got a little LED. So LED is a diode. Light emitting diode. It's diode. It's gonna emit light. You run the current through it, it's gonna emit light. It's LED. Okay? So because the internal resistance of that guy is super low, for example 10 ohms, super low, if you supply this guy with a 5 volts without a resistor here, what's the current gonna flow through it? Okay, now it brings up the terms for you guys to answer. What's that? Half an amp. Is that half an amp? No, it's gonna be I equals 5 volts divided by 10 ohms, right? If we don't have this resistor, just a wire. The current will be I equals 5 over 10. right? Because I equals V over R, right? Okay. So the current will be 5 volts over 10 ohms, which is, yeah, half amps. But usually we don't say that.
5 amps.
Yeah, we say 500 milliamps. Okay, that's more common, but half amps is also right. But usually we say 500 milliamps. It's a lot for LED. So it's gonna either reduce the lifespan of the LED or blow it up directly, depending on the current rating of the LED. You can look it up in the data sheet. It's bad. So what you wanna do is add a current limiting resistor. Usually up to 1K, let's just say 1K ohms. So you can reduce the current significantly to protect the LED. But definitely if you have a 1K resistor in series with the LED, what's gonna happen to the LED? It's gonna dim it, right? It's gonna dim it. But it's okay. As long as it's not being dimmed to a level that you couldn't see, it's just serving your purpose, right? If you can still see it, it's pretty obvious, it's okay. So what if you put a 1K resistor, it's too dim? What's gonna happen? What you wanna do for that?
Use a lower resistor.
So what's the resistance you wanna use?
How many volts do we want to send to the LED?
How many voltage? We usually don't consider
Or
that.
how many amps do we
How many amps? How many currents? How much currents? Current, right? So just look at the paper. What's the range of the LED you're gonna use? Usually for low voltage stuff, digital stuff. Like I said, right? Here, that's a sweet range to use. If you grab a 50 ohms resistor, should I blame you? Before taking this class, yes. After taking this class, no. Oh, the other way, actually. Anyway, so nothing below 300 ohms, okay, for digital stuff. Okay, just 300. Just grab a 300 ohms, 500 ohms, 800 ohms, 1K. It's okay. All of them are fine. You know, you can always adjust it if it's too dim, too bright. Usually they will be fine. All right. So the equations are these equations. Are there any other equations? If you integrate Q over time, I over time, which are getting Q. So if I is not a constant, you got an I like that. Here's I, here's T. And you wanna calculate the overall Q. Coulomb, yeah, just to integrate. So this must be I is the function of T, right? It just plug this guy here and have all the bonds. It could be 0 to T, okay? Just integrate it. Okay, any questions by far?
How often will we be dealing with a nonlinear current?
Nonlinear currents will be the last 4 weeks of the semester. Will be caps, right? Caps and inductors. You got inductors. Okay. Let's grab some problems to talk about, to discuss, okay? Oh, units. Nano is 10 to the negative 9. Micro, 10 to the negative 6. Milli, 10 to the negative 3rd. Atto, 10 to the negative 18th, I think. Femto, 10 to the negative 15th. Pico, Pico is a side. 10 to the negative 12th, right? Jar, you can find in the jar. So that's 10 to the negative 12th. So these are the
all
U.
the major ones.
Hmm?
Right? Those are all the major ones.
Oh, the major ones, yes. Anything else? I think I have never seen. I only see this one once. Over here, So the most frequently used ones are these. Oh, also, 10 to the third will be kilo. This is something you know. 10 to the sixth will be mega, depending on which context. In digital, it's mega. In somewhere else, will be million, right? A billion or giga, but you know it's not exactly mega or giga because it's using 10 to the 2 to the 10 in digital. If you take logic, you'll learn that. Anyway, what is this? Trillion, yeah.
Right? Or tera?
Tera, yeah, tera or trillion, right? So if it's just a 10 based, it will be trillion. A trillion. Tera will be 2 based. It's not exactly the same, but okay. And the standard units will be joules for the energy, watts for power, voltage, amps, ohms. Am I missing anything? Coulombs. Seconds. So this one is power times t, right? Or integration of power over t. This is V times I. This is I times R. This is V over R. This is V over I. Charge is I times T.
It's just a base unit.
Yeah. Oh, there's another one called Siemens. Siemens. No, it's conductance. It's simple. It's just 1 over ohms. You will see this as G, I think, or S. S is a unit. So this will be smaller s. This will be a uppercase s, I think. But however, the unit is, no, the symbol is G. So it's usually like G equals something Siemens. If I use my teaching material, I will never use it. I will never do it. Very rarely used. What's A? A is amp. Good question.
It doesn't say it's I.
Yeah.
Yeah, it's ampere. Yeah, so we use, it's like something you put on the left-hand side of the equation, right? So I equals something A. You know what I mean? This is the unit. This is the name or symbol, or it's not a unit. You are not saying it's 3I. It doesn't make sense. It's 3 amps. So I, the current, is 3 amps. It's confusing, right? We usually use V as a unit and something on the left-hand side, the name as well. So like a V1 is 3 volts. I1 is 3 amps. Q1 is 3 coulombs. E1 is 3 joules. They sometimes use omega as well. P1 is 3 watts. W1 is 3 watts. R1 is 3 ohms. G1 is 3 Siemens, which is 1 over R. It's easy. Conductance. Conductance. It's describing the conductivity. So the resistance is the resistance, right? Resistor, resistance. is how much is resisting. But conductance is how much is conducting as a current or voltages. Conductivity, just 1 over ohms. Reciprocal of ohms. Any questions? No question or stupid question. Any questions? You're helping other people as well if you ask. What's that?
So is power the same thing as work in this case?
Power is the same thing as what? W?
Yeah.
Right? Yes. So these are P, sometimes the power is 3 watts. W1, sometimes they also use as power, is 3 watts.
Okay. So
Usually we use P. P is more common.
P is the same thing as W.
Yeah. But you'll see a lowercase, it's not W, it's omega, it's a lowercase W a lot of times. Like this, reading like that.
And in that case, it's
That's energy.
Is there a reason why omega is so common for energy?
Omega is so common.
Yeah, why is omega the sum of pictures?
Oh, because the size of the memory. So we describe the units of the memory usually described as bytes, right? Bytes. If it's an 8-bit computer system, so 1 byte is 8 bits. 8 bits is 2 nibbles, and you usually so in the very old days we use bytes as a unit memory, basic memory units. So it's 1 byte as 1 memory row. So a lot of times we need a lot of memory space. So you just replicate that one to like millions of memory banks. So you are getting like a megabytes, gigabytes, and also since we are running computer systems really quickly, so usually getting to the megahertz, gigahertz region. That's why. Good question. Okay. There's another term called power balance. Power balance. I'll directly just show you the picture. I know it's small, but I'm gonna zoom in. Could you see this clearly on the back? Okay. Okay. So I'm gonna hide the solution here. Okay, let's look at this problem. You see it's been labeled all different ways, Let's look at the first one first. VA, like I said, you can label any way you want. You label it that way, it's giving you a negative voltage. See A? It's a negative voltage. But it's telling you it's plus minus. So what does that mean?
So it's just flowing in the opposite direction.
Yeah, from left to right, it's dropping minus 25 volts. So what's the method? Like what I said at the very beginning of class. Convert it to the physical. Convert to the physical is a real circuit, it's real voltage, real current. So if it's plus minus, which means from left to right, it's minus 25 volts. So the real voltage drop will be from right to left, which is 25 volts, right? Is that clear? Okay. Is that clear? So for A, let's just talk about A. I'll just label it. I'll just do it. When you guys are doing this problem, just draw it and label it. So that's the real voltage drop, which is 25 volts. Okay. What about current? Current. They label it that way from left to right, which is 13.75 milliamps. See, milliamps, right? So milliamps. 13.75 milliamps. Is that the physical current flowing through the component?
Yes.
Yes. Why?
Can't see it.
It's positive.
Oh, sorry. It's pointing that way. It's positive. No sign change. It's going to be the physical current flowing that way. Okay? I have a question. Hey, this one has a drop from right to left. That's a physical drop, 25 volts. And on Monday, Dr. Lee told us if there's a current flow through it, the drop should go from left to right. right? Like Ohm's law, like what we said on Monday, is you run the current through it, you got a voltage drop from left to right. But why we are having a different current? It's physically it's dropping from right to left, but the current is flowing a different way.
Providing power.
Yeah, because you have other components in the circuit as well. They're pushing. Okay? It's not just one component. Others are making a combinational effect to the current. Why? Because if you have a higher potential here, a lower potential here, the current is going to flow that way. Okay? So, is this one absorbing or dissipating power? Or supplying? Supplying, why? The current is flowing out from the positive terminal. If you consider this is the battery, is the anode. Anode is sending current out. So it's supplying, it's delivering, right? So we're getting a negative power. Negative power. Okay? It's okay. So when I'm talking about negative power, it's just serving that problem. If it's asking you, what's the power of this guy? It's a negative power. For calculation, it's a negative power. Okay? It's just a negative power. It's delivering, it's sending out power because the current flowing out from the anode. If you consider this as the battery, this is the anode of the battery is sending current out. So that's why it's delivering. So we're getting a negative power, which is negative 25 times 13.75. Right? What's the unit? Yeah, milliwatts, right? Why? Because it's a milliamps. Because it's milliamps. So that's why it's a milliwatts. Right? So just keep doing that for all the components in here by looking at the table. So sometimes you are getting negative power, sometimes you are getting positive power. Where did you add a sign? Where did you add a sign? How did you add a sign? Remember? Where and how? So we are doing PA, right? PA is this. I get a physical voltage, I got a physical current. They are both positive numbers when I'm dealing with this problem. 25 times 13.75 is a positive number, but I manually add a negative sign over here because I know it's delivering power to the outside circuit. So that's how I add it over here. So eventually you are getting something, it's a negative something milliwatts. For this component, you're getting PA, I get a PB, P something in the future, and you add them together, all the P's. And you're getting what? 0. That's called power balance of the circuit. So you have a couple of problems in the homework assignments are asking you to check the power balance. How do you check the power balance? You have to know the voltage and currents of each component. Okay? Then you just use the voltage times V times I to get a power. And then you have to determine if it's delivering power or absorbing power in order to add a sign to it. And then add them together, see if they equal 0, okay? If it is 0, it's balanced, it's checked, balanced, checked. Otherwise, it's not. Something wrong with it. Something wrong with the calculation. There's nothing wrong with the circuit. It's operating, right? Something wrong with the calculation. Anyway, any questions for this? No? Okay. 5 more minutes. Let's grab another problem. They are all very similar. Yeah, I think what I talked about at the very beginning here will solve probably like 50% of the problem. It's just all repeating. If you understand what's going on, if you know how to do it, convert it to the physical voltage and currents, you should be able to do most of the problems. If it's not the case, let me know, okay? Email me, email the TA, visit during office hours, all this kind of thing. I think that's pretty much everything for tutorial 1. Yeah, that's it. That's it. Homework 1. Is that due? So tutorial 1 is due Friday? Homework 1 is due Friday. No, I mean that's it for tutorial 1. We still have 4 minutes. Sorry. Now let's look at homework 1. Homework 1. Oh, electrons. Charges, electrons. You learned that in physics. I'm pretty sure you learned that in physics. One more point. You'll see all the circuits in the home problems. They are just a loop. They don't have a ground, which is wrong. But it's okay for beginners, for circuit 1. You know, for a circuit, you need a ground. Using LT Spice or any other simulators, if you don't label a ground, it won't simulate. So you need a ground. You need a reference point. Okay? But if you see circuits without a ground, it's okay. It's okay because just for you guys, it's just on the textbook for you guys to calculate the currents and everything in it. Sometimes the circuit can start getting complicated. You know, towards the end of the semester, you'll see multiple resistors and things like that, right? Okay, still no ground. For calculation wise, it's okay, but you should know that usually for most common cases, we ground where? We ground the cathode. Why we ground the cathode? We ground the cathode of the battery. If you use a benchtop power supply in the lab, this class doesn't have a lab, but if you're doing working in the lab, you got a black terminal and red terminal. You can set up the voltage power supply. For example, you set 5 volts. Set 5 volts for the power supply. It's just like a battery. So red node is plus, this is minus. It's just like the battery's anode and cathode. Okay? So you have to connect it to the circuit. You got a circuit here. So where do you ground the, and you connect to the common ground of the circuit. This is the common ground of the circuit. The reason we ground the cathode is what? Why do we ground the cathode?
So we can know the exact potential and our voltages for
Yeah.
the battery.
Yeah? What you want to say?
Convention.
Convention, yes, it's convention, and combine the two answers will be perfect. We'll make it perfect. It's convention. We ground the cathode because we'll exactly know
How much it can.
how much is supplying the voltage to the circuit. Exactly. Because all the voltages are relative. If I'm supplying a 5 volts from the power supply, we know that it's the voltage difference from the red to the black. Okay? That's what we know. We set up 5 volts, boom, turn it on. So immediately there will be a 5 volts difference from the red to the black. So it's going to be V red minus V black will be 5 volts. If you ground black, you are getting 0 here, right? So what you know? This will be 5. So you are supplying 5 to every single component. If you see the component has a 5 volts voltage rating, and you need to use exactly 5 volts to all the components in the circuit. That's how you set up a baseline, and supplying the exactly correct voltage to the components in the circuit. Okay, that's everything for today. We'll see you guys on Friday.